Uh-oh. I got it for you then. Oh, maybe I don't got it. I'm feeling rejuvenated, full of energy. What about you? Are you tired? Are you ready to go? No. Okay. Let's try this. How is it possible if I've got one atom here and another atom over here, remember the center of these atoms, what kind of charge exists at the center of an atom? Proton. Yeah, there's lots of protons, aren't there? So is the center or the nucleus of an atom, is it positively or negatively charged? It's positively charged, right? So both of the centers of these are both positively charged. How is it possible that I can get this thing to be attracted to that thing? Yeah. Surrounding them are what? Valence electrons. Not just valence electrons, but the outer energy level has valence electrons in them. And remember that if we stick a couple electrons in between these two things, these positives are attracted to these negatives, these positives are attracted to these negatives, and the electrons form the glue that holds these protons together, right? Do we remember kind of going over that? That every single chemical bond is made up of how many electrons? Two electrons. And that's all you need. That's all you need to glue two atoms together, right? Of course it's possible to rip these atoms away from each other. That's what a chemical reaction is. A chemical reaction is the rearranging of atoms to form new bonds with other things. Okay, that's totally fine. So let's think about this. Remember, those electrons are from the valence shell of the atoms. Well, that means we should probably take a look at the valence electrons of a bunch of different substances or atoms. So let's take a look at beryllium, nitrogen, argon, and aluminum. I want you to quiz yourself. I want you to try and see if you remember how to make the Lewis structure of these elements, these atoms. Do you want to do one together?
Yeah, I just forget what it was.
Yeah, okay. Beryllium. Remember?
What's the one?
Yeah, it's the one with the dots. Beryllium, if we look at beryllium, how many electrons does beryllium normally have?
2.
It's got 4, but remember, it's got 2 in the first energy level and 2 in the second energy level. But which ones do we care about? The valence shell. We care about the outside ones, right? So what was the shortcut to figure out how many valence electrons something has? Wim, thank you for putting your hand up. Yeah, you just figure out what row they're in. So which row is beryllium? Is it in the first, the second, the third, the fourth, the fifth, the sixth, the seventh row? It's in the second row, right? So it's in the second row, and how many do we have to count from left to right to get to beryllium?
2.
1, 2, right? So beryllium has 2 valence electrons. In general, from a really general perspective, how many bonds can beryllium form?
2.
It's got 2 bonding electrons, right? So it can form 2 bonds. Yeah, no problem. Okay. How many lone pairs does beryllium have?
0.
It's got none, right? We only care about the valence electrons. Let's take a look at nitrogen. When you look at nitrogen, how many valence electrons does it have? Yeah, when I count, right, which energy level, which row is it in? It's in the second one. And so when I count across, right, 1, 2, 3, 4, 5, nitrogen has 5 electrons. Let's put 5 electrons around here. 1, 2, 3, 4, 5, right? Why no? How many places are available? Only 4. There's only 4 orbitals, right? And each energy level. So 1, 2, 3, 4. And once I put them all, right? 5. How many bonds, loosely speaking, how many bonds can nitrogen form? 3. Typically nitrogen can only form 3 bonds. Now, that doesn't mean that all the time it only forms 3 bonds. I'm just saying, under most normal circumstances, it only forms 3 bonds. Wim, question? Okay. Argon. How many valence electrons does argon have? What energy level is it in? What row is it in? It's in the 3rd row, and it's all the way across. So how many electrons? 8. 1, 2, 3, 4, 5, 6, 7, 8. That looks terrible, but whatever, that's fine. So how many bonds can argon make? Under normal circumstances, right, most regular circumstances, 0. There are some rare cases where if you really put this argon under a lot of stress, under some weird conditions, yeah, maybe it'll give up some of its electrons to bond, but most of the time it won't. Aluminium, how many for aluminium? 3. So how many lone pairs does aluminium have? 0, but 3 bonding electrons, right? How many lone pairs does argon have?
4.
It's got 4 pairs of electrons, right? It's like you're wearing 2 socks, but it's still a pair of socks, right? So, okay, all right, perfect. Now, what if I said we had a nitride ion, which is N3 minus. Let's think about regular nitrogen. How many does regular nitrogen have? 5. 1, 2, 3, 4, 5.
3 extra.
Does it have 3 extra?
Yeah.
Or did it give up 3?
It's the opposite of the sign says.
It's the opposite of what the sign says. The way I think about it, it's the opposite of what the sign says. The way I think about it, are electrons negative or positive? This represents what you have extra. You have extra of these. So if you have extra negatives, that means you have extra electrons. How many extra electrons? 3. So where would those 3 electrons go? 1, 2, 3. And what would we put around it?
Brackets minus 3.
Right? We would say N with it's now it's got a full octet because it's a nitride ion. We put square brackets around it and we say it's 3 minus because it's an ion now. Okay, perfect. That basically, pretty much, that brings us all the way up until the stuff that we talked about on Friday. 3 Fridays ago. Remember, 17 days ago. Okay? So 3 Fridays ago, that was pretty rough. The next section, the next little bit that we started talking about, it was all about polyatomic ions and molecules. Right? how can we arrange all of the atoms and all of the electrons in a molecule? That was the idea. So when we're thinking about molecules or polyatomic ions, let's just dive right in. Let's just see if we can remember a little bit about this. I wanna just talk about a compound. The compound is sulfur dioxide, SO2. Now, I don't know if you remember, but there was a list of instructions. If we wanted to make sulfur dioxide, if we wanted to make this compound, then we had to, put a central atom, and then we had to put the peripheral atoms. Do you remember what peripheral means? On the outside, right? Your peripheral vision. I don't know if you noticed, but I went and got an eye check, and I had to check my peripheral vision, and it was not good at all. That's okay. So your peripheral vision is the outside, these peripheral atoms. And then we had to add some electrons here or there, and we had to backfill if we needed to. Do you remember anything about that? Ooh, it's pretty washy. Okay, that's all right. First thing we want to do is we want to count all the valence electrons. Number one, let's count our valence electrons. So how many valence electrons are there going to be in SO2? How many S's? No, that's okay. How many S's are here? There's one, so there's one S. How many oxygens are here? Two. If I had one S, how many valence electrons would that be? Remember, we only care about valence electrons. Okay, well, oh yeah. This is 6, right? One sulfur is 6. Are we all in agreement with that? One sulfur is 6 valence electrons. 1, 2, 3, 4, 5, 6, right? And then what about oxygen? Is also 6, but 2 times 2 is 12. So that's 18 valence electrons. Now, the second thing that we did, right? Okay, count your valence electrons. Good, no problem. Number 2, so the second thing we were supposed to do is put the central atom in the middle, put the peripheral atoms on the outside, and just bond them together using electrons, right? So central atom in the middle, bonded to the peripheral atoms. Which one of these do you think probably they're trying to tell us which one of these is the central atom? Do you know which one it is? It's the sulfur. They're trying to tell you that it's the sulfur. Now, it's not always the first one, right? But a lot of the time it'll be the first one. Usually it's the one with the highest bonding capacity. The trick is here, sulfur and oxygen have the same bonding capacity, so, okay, whatever. So we're going to put the sulfur in the middle, and we're going to put the oxygens surrounding it. And what do I have to put in between them? A bond. Remember, a bond is how many electrons? 2 electrons, right? So, how many electrons have I used up so far? I've used 4 electrons so far. So out of 18, 4 are gone. What does that leave me with? 14. That leaves me with 14. Do you remember, we're going to start putting electrons on something. Should we start with the central atom, or should we start with the peripheral atoms? We start with the peripheral atoms. I've got 14 electrons left over, right? I had 18 and I used 4, so I got 14 electrons. Let's put our 14 electrons somewhere. 2, 4, 6, 8, 10, 12. 12 of my electrons that I had left over are gone. So how many electrons do I still have left? 2. I've got 2. I've used up 16 so far. 4 here and then those 12. So I've used up 16. What's the only other option? I'm going to put it on the sulfur. Now there's a problem. Do you see the problem here? Sulfur's valence shell is not full. Is there any way at all that we can move some electrons so that everybody's happy? Remember, everybody has to be totally happy here. Wim? So does one of these oxygens, does it have some electrons to spare? Yeah. Now we don't want to give away the electrons totally, right? We don't want to take these electrons and just pass them off, because what's the problem with that? Then now the oxygen doesn't have a full shell, right? So what's the way that we can do this so that we can have them?
Double bond.
Yeah, we're going to bring them in between both, right? I'm going to bring them in between both. So now, can you see how there's a double bond in between the sulfur and the oxygen? How many electrons surrounding this oxygen? 2, 4, 6, 8. It's happy. How many surrounding this sulfur? 2, 4, 6, 8. It's happy. How many surrounding that oxygen? 2, 4, 6, 8. This is the Lewis diagram. This is the Lewis structure for this molecule. Instead of drawing the Lewis diagram, we could draw the structural diagram. It's the exact same thing. We draw lines for bonds and we ignore lone pairs. So it's still the same structure, would you agree? The S in the middle with the O over here and an O over here. What's bonding this O and that S? A double bond, right? And I would say a double bond is, we call it a double bond. It's made up of 4 electrons, but it's a single unit of a double bond, okay? It's kind of complicated, but these bonds, they behave as if they're all kind of the same thing. Wherever one bond goes, the other part of the double bond goes. What's connecting this sulfur and the other oxygen? A single bond, and then we just ignore all the lone pairs, right? Boom, done. Swish. Are we okay with that? Yeah? All right. That's no problem. So let's try something a little bit more complicated. Just a tiny little bit more complicated. It's the exact same process, but instead of doing sulfur dioxide, what we're going to do is we're gonna do a hydroxide ion. And remember, your steps for solving these problems are all in your 3.2 notes, right? This is the 3.2 package. So they're all here, right? Count the valence electrons, identify the central atom, draw the bonding electrons, fill peripheral, fill the central, move the lone pairs in if you need to, write the charge, blah, 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 blah. So let's do a hydroxide ion. What is the formula for a hydroxide ion? It's OH minus, right? Sorry, I keep moving this around on you. It's OH minus. So what was our first step again? Do you remember what our first step was? We want to count the valence electrons. So let's count the valence electrons. There's one oxygen and there's one hydrogen. It would be 7, wouldn't it? If it was OH, it would be 7 electrons, right? But it's not OH. It's OH minus, right? Jana, what does that mean? What does that charge of -1 mean? Yeah, we have an extra electron, don't we? So the oxygen represents 6 electrons. The hydrogen represents 1 electron. But because of that minus sign, right? That's an extra electron. So instead of 7, it's 8, right? It's 8 now because of that negative charge. Okay. Well, let me be very clear. There's only 2 atoms in here, right? It's hard for there to be a central atom if there's just 2 atoms. Do you understand what I mean by that? Yeah, okay. It's like one's on the left and one's on the right, but there is no center. So, okay. So the O is going to be here and the H is going to be there. Okay. What do we have to draw in between them? Yeah, we got to draw a bond, right? That's 2 out of my 8 electrons gone. How many electrons do I have left over? Are you going to put some of those 6 electrons on the hydrogen or on the oxygen?
Oxygen.
You're definitely not going to put them on the hydrogen. Why?
Because it's full.
Because hydrogen can only fit how many in it? It can no. It has one. It has one to start with. But Luke, what's the maximum number of electrons that first energy level? Yeah. So hydrogen is full right now. Would you agree? Hydrogen is max capacity. So the only place we can put it is here. Are we done?
No.
Kind of.
Need the bracket.
Yeah. Why? Why do we need the brackets? Because it's an ion, right? So that's, what is this? Is this the Lewis structure or is this the structural diagram? It's the Lewis. The dots represent Lewis, right? Anytime you're drawing the dots, you're drawing a Lewis diagram. I could turn this into a structural diagram by doing this. Now let's be very clear about this. This is an ion, but the ion, does this ion have bonds inside of it? This ion is held together by something that we're going to call covalent bonds. Okay? It's totally possible for there to be covalent bonds inside of an ion. And we'll talk about that a little bit more towards the end of class. The difference between a covalent bond and an ionic bond. Okay? What I want you to do, if it's okay with you, is I would like you to do some practice. Okay? Do you want me to guide you in some more practice? I don't think we need that much more guided practice, okay? So what I want you to do is I want you to do, this is the last page of your notes. This is the last page of your 3.2 notes. And you should have tons of space either below or on the back side. Would you agree? There's tons of space on this notes package. I want you to do 5A E and 6E. Okay, like that's 3 examples. I want you to make the Lewis diagram and the structural diagram for those 3 things, okay? let me know how I can help. I will be wandering around. Oh yeah. Yeah. Thank you very
You picked the one with the that can have the most
That's fine. Yeah. So did you figure out how many electrons? Nope. There's one carbon, so that's 4. But there's 2 sulfates. So how many is that? Good. So start with the carbon. Oh.
I think it's the C.
No idea if this is any. This is like the same brand. Oh, yeah. Okay, that's 4 out of your 16. So how many do you have? 12. So put your 12 around the center. Good. One lone pair for each of those. Right. Carbon is 4. Because hydrogen can have more than 2, right? The way they're, and I really wanted to put this in there because it's trying to tell you the CH3 is a group, CH3, and then what comes next? And then SH. Okay? That's the formulas trying to hit you with that.
I got 30. I am really not. Yeah.
Yes.
You're on the right track, but you're not good.
Okay.
Yeah, I know.
I literally.
So what's
I love that. You're so blessed.
Look at the sulfur. How many surroundings?
I got scared these
pairs of electrons, they belong both to the sulfur. So they're being equally shared. Sulfur is carbon.
Is that 18?
Sounds like. Why did you say?
No,
Yeah, that's all you needed, man.
Wait, what? What did you
Okay, but you're not done.
Yeah, take it over.
2, 4, 6, 8, 10. So you have 4. Well, that's, you want to put them on the equal right? That's hydrogen. It's like the centralized.
That's what everyone's wondering.
Where's the only other place? The sulfur only has 4. You have 4 extra electrons. That's 4 in hydrogen.
It is a nice.
How many electrons do you have? No. Because the one carbon is 4, 2 sulfurs is 6 each, so that's 12. 12 plus 4 is
Show me where you
Now, how can you do that? How can you make it Okay, I'm gonna stop you in 2 minutes. What? Oh yeah. PO4 with a 3 minus charge. So how many phosphorus is? How many phosphorus? How many P? 1. Okay, good. How many oxygen? 4. Good. And then you add 3 once you've added it. You're not quite as
Oh, yeah.
that's the tiny thing. Okay? Very good. You have to look at it.
Oh!
It says 6, but it's only 4 valences, right?
Oh, okay.
20, okay, but it's 22. And then there's 2.
I think I need this. Holy crap. I can see clearly.
And this is a really like weak prescription, but it does. Can I say it out the same?
Try it once.
What
is that?
Yeah, I mean, the distinguishes are, they said particularly in the left eye, so in my right eye. Okay, let's try this. It looked like most people were pretty confident. You know what I mean? You're like getting there with this kind of stuff. Was drawing the Lewis and structural diagrams for these ions and molecules, was it okay? Once you get used to the process, it's not too bad. Let's do carbon disulfide. So when I do carbon disulfide, that's 4 plus 2 6s, so 4 and 12 make 16. So we got 16 electrons to go around. So carbon disulfide, 1, 2, 3, 4. So I've used 4 out of my 12. So we're 4 out of my 16. I got 12 left. 2, 4, 6. 2, 4, 6. And I'm done all my electrons. I've got no more electrons to go around. But the big question you have to ask yourself, is everybody happy?
No.
No. That central carbon is not happy. How can we make that central carbon happy? Yeah, we can get rid of those ones, get rid of those ones. So we're going to pull these electrons in here, pull these electrons in here, and that is the Lewis diagram for carbon disulfide. Let's do the structural diagram. A carbon in the middle, and what's surrounding it? Two double bonds on either side, right? Good? Nice. Let's do, it was methane thiol, CH3SH. Now, do you remember the trick here? Like there's a little tiny trick associated with this. What's the formula trying to tell you is the central atom? It's trying to tell you the carbon's the central atom. And what's surrounding the carbon? The 3 hydrogens, and then it's an SH as well, right? So it's the 3 hydrogens, and then it's an SH. That's why we say, instead of saying CH4S, we try and say CH3SH, because it's almost lumping the SH together, right? Well, when you do this, you basically end up with that, right? The carbon is bonded to the sulfur, and then you fill in the gaps with the hydrogens. Was that okay? Yeah. The last one was the carbonate ion, CO3 2-. So we got 4 and 18 is 22. Is it 22 electrons?
24.
It's 24 electrons, right? Okay. So a carbon with 3 oxygens surrounding it. 2, 4, 6. So 6 out of my 24 are gone. That means I have 18, right? 18 electrons left. 2, 4, 6, 8, 10, 12, 14, 16, 18. So I'm done with my electrons. I've got no more electrons, right? But is everybody happy? No, not everybody is happy. See, it doesn't matter which oxygen you steal from. Not steal from. Doesn't matter which oxygen you share with. Yeah, sure. Yeah, the center one would be nice, right? But it doesn't really matter. We haven't talked about the three-dimensional shape yet. We'll do that tomorrow. But, perfect. Is that 100%? Right? Carbon bonded to some oxygens, bonded to another oxygen, 2 months. Good. So Lewis diagrams, structural diagrams. Are you feeling kind of confident? No? Yes? Kind of, sort of? Okay, that's where I'm going to finish with our practice. That is what the quiz is on tomorrow. I will give you 2 either compounds or polyatomic ions, and I want you to make the Lewis and structural diagrams for the compound or the polyatomic ion. I'm probably going to give you 1 compound and 1 polyatomic ion. Probably, yeah.
What's the letter with the dots called?
That's just a Lewis diagram.
Okay, sorry.
Yeah. So the Lewis diagram for example, the Lewis diagram for phosphorus is P with 5 dots.
But then
Right?
that's also a Lewis diagram?
Yeah, this is also a Lewis diagram for a molecule this time,
Okay.
or a Lewis structure we could call it. Yeah.
I'm not person.
Just depends on if you're talking about an atom or if you're talking about an ion.
What do I do?
Good. Cool. Nice. I'm going to move on. Ooh, I should hand these out before I do anything else. 1, 2, 3, 4. Hey, yeah, it is quite short.
Why are all the major assignments in
What?
Why are all the major assignments?
All of the major assignments should be in Power School.
Why are the marks on?
Well, the Chapter 4 ones, the ones you literally gave me at the beginning of the semester, I had them stored away until I felt like doing them, because a lot of people showed up that day that they were due and they didn't have them done, and I was too lazy to mark them until kind of now.
All of them.
Really? Okay, can we talk about this just a little bit later? Yeah. Okay, that major assignment that I just handed you is due Monday. Well, yeah, 7 days from now, Monday. It's due Monday, and we're going to mark it at the end of the class. So I'm telling you right now, we're going to mark it at the end of the class. Not at the beginning, but at the end. Jared, you have your question? Ooh. Maybe that's because I counted out 8 instead of 10. Howdy.
In the middle of teaching?
Nah.
Just having fun.
We're just having fun.
Like 2 screens.
Yeah.
Anything that talent is left
Yeah.
or,
Like saying.
no, the drawing isn't there. When you have it on your main screen, you want to click
What you can do is you can just switch, if you're okay with it, you can just and so everything.
No, but I mean, I don't think everything except that it's 30, I want it to be the way it is. There's no quick fix for that.
I don't use it. Let's try. If you have a couple seconds. Just give me a second. Sorry. So you.
The thing, the play button is there.
And it shows up there, and it doesn't.
Drag it across.
Is that because? Can you do this? Nope.
Tried it.
That's so stupid.
Click up on slideshow.
Where do you see?
Across the right top.
Oh, in the red. So now it's showing up on your primary. Or there's two options there, right? Yeah, so just click whichever option you need to. Either primary or whatever. Okay, my apologies about that. My sincerest apologies. So hopefully everybody caught that. The assignment is due next Monday at the end of class, right? That major assignment.
Oh, that's okay.
I didn't put it up yet. I didn't change it. Yeah. I do remember, but I haven't done it. I've got a little post-it note at my desk. Bug me, like seriously bug me, like throw something at me if I Hey, do you remember talking about this? The tug of war? No, you don't remember talking about the tug of war? So remember, there's a nucleus. Every bond exists between two atoms. And so there's an atom over here. There's an atom over here, and the nucleus of the atom is positively charged. There's another atom over here. The nucleus of that atom is positively charged. And there's two electrons in between them. And remember, some of these... Oh, did I give you way too many? These electrons are... There's a battle. I knew I didn't screw that up. Okay.
Well, now I got two.
There's a battle between these two nuclei for the electrons. Sometimes they're equally shared. Sometimes one person is winning a little bit, and sometimes one of the nuclei wins outright, totally wins. So remember, one of these electrons comes from one atom. One of these electrons comes from another. So each atom contributes one electron to this bond. Would you agree with that? I have my electron, John has his electron, and we can both share our electrons together. That's how we complete our octet. But the problem is, if I show up to this relationship with one electron, and then I steal both, how many did I actually steal? I only stole one. I know I took both, but one was mine to begin with. Does that make sense? Yeah, so when you win, if you outright win the battle for the electrons, you really only steal one electron, okay? If both atoms are pulling really hard on the electrons, if they have high electronegativities. Give me an example of an element that has a high electronegativity. Wim? Carbon, let's see. What is carbon's electronegativity? It's 2.6. Is that pretty high when you look at all of the elements in the periodic table? Yeah, I would say a lot of them, right? A lot of them are in the mid-2s. Some of these metals have pretty low electronegativities. Some of the non-metals have pretty high electronegativities. But yeah, 2.6 is it's on the higher end, right? What? Fluorine is pretty big. What's fluorine's electronegativity? 4.0. Is there any element higher than 4.0? No. That's the one element that pulls the hardest on all of its electrons. Remember, it's because it's so small, the electrons are held really close to the nucleus, and it's got a lot of positive charge inside that nucleus, so it's got a strong hold on the electrons. Okay, in this tug of war, most of the time, because neither nuclei wins, they end up sharing the electrons. What's it like if you share the ownership of a restaurant? You would be the co-owner. Does that make sense? Wim?
How much harder would how much higher would the electronegativity have to be on one thing to rip the electrons away?
We're going to talk about that. We're going to talk about the threshold. We define it that the difference, if the difference is greater than this, we say one of them has just won the battle. It's just all the time the electrons hang out with that one thing. Okay, this is a covalent bond. If you and I are sharing electrons, and I'm trying to win the battle, and you're trying to win the battle, but nobody's actually winning, that's what we call a covalent bond. They're sharing the valence electrons. This occurs between atoms that have a difference of electronegativity less than 1.7. So let's take a look. What type of bond exists between hydrogen and oxygen in water? And, okay, so let's draw water. What's the electronegativity of hydrogen? Electronegativity of hydrogen is 2.2. What's the electronegativity of oxygen? 3.4. So what is the electronegativity difference? I used delta. Has anybody ever used delta to show difference before? Yeah, you should have all used it, actually. Every single one of you.
I just put it,
You've never seen that before? When you're doing slope calculations?
Oh, yeah.
Slope is delta y over delta x.
Oh, yeah.
Rise over run? Well, you've all done science 10, so you've all done it before, right? It's the change in electronegativity. Okay, Wim, you had your hand up. Yeah, it's 1.2, right? The difference is 1.2. Now, I kind of skipped some stuff. And I just wanted to jump in. There are 3 types of intramolecular forces or bonds, okay? There's covalent bonds. Covalent bonds are when we have a difference of less than 1.7, right? That's what we just talked about. Ionic bonds, well, what do you think that's going to be?
More.
And if it's exactly 1.7, then it kind of goes either way. It's pretty ambiguous in that case. And then that's metallic bonds, and that's two metals bonded together. And we'll talk about that. We'll talk about two metals bonded together.
Would that be like more better that it's one still away, so it's negative?
No, it's we'll talk about it. Okay. So would you agree? Whoa, that was weird. When I look at my bond, when I look at my water molecule, what's holding the oxygen and the hydrogen together? What's bonding these things together? Yeah, it's a covalent bond. What's a covalent bond made out of? Two electrons, right? This bond it symbolizes two electrons, right? So what that means is that these two electrons are holding these two nuclei together. There's a force holding these two nuclei together. There's an attraction between this positive charge and that negative charge, and this positive charge and that negative charge, right? That's what a bond is electrons gluing these nuclei together. So there's a force inside of this molecule. Do you remember, have you ever used the prefixes intra or inter before? International. Do you know what that means? No. Not more than one, but between two, right? International means between two that are separate, between two nations. What would be intranational? Inside one nation. Okay? So when I say the words intramolecular, what does that mean? Inside the molecule. There's a force inside the molecule holding these atoms together, and it's a bond. It's a covalent bond. Okay? That was a lot of work to get here, but it's kind of important. Intramolecular forces describe the bonds, and the bonds that you're really familiar with, or you should be familiar with, are usually covalent bonds. Covalent bonds are anything that has a delta, or a difference in the electronegativity of less than 1.7. So what is this? This is a covalent bond. Is the hydrogen or the oxygen, is one of these things outright winning the tug of war for the electrons? Is anybody totally winning? No, they're sharing it. This difference isn't big enough for somebody to win. Who's kind of winning the battle? Oxygen is pulling harder. So that means the electrons belong more to the oxygen than they do to the hydrogen. Do you kind of agree? It's like if you're winning the battle, the flag's closer to you. It doesn't mean you won. It doesn't mean you stole the flag. It just means it's closer to you. That's all. This really screws up a lot of people. Yeah. Kind of looks like a cell, but it's not. Okay? This is a nucleus, and this is another nucleus. The bubble that surrounds these two nuclei, that's where the electrons could exist. I don't know if you remember back to Science 10, but in Science 10 you would have talked about an electron cloud model of the atom. And what it means is that the electrons in this bond, they can exist here or here or here or here. They technically exist everywhere until we go to look at them, and then all of a sudden they show up somewhere. Okay? It's a really complicated model of the atom, but it's basically showing which one of these nuclei hold the electrons for longer. Is anybody winning? Can you see, is the bubble closer to one than the other? No. Or is it pretty even? Even. It's pretty even. This is what we call a non-polar covalent bond. It's brought about because the electronegativity difference is very, very small, or it's 0, okay? Let's take a look at an example. Let's look at chlorine. A molecule of chlorine, Cl2, contains 2 chlorine atoms. Cl bonded with Cl. What's the electronegativity of chlorine? So that means the other one is 3.2 as well. Who's winning this battle? Yeah, what's the difference?
0.
It's 0. So do you agree that there's both of these chlorines, they're equally sharing the electrons? Nobody's winning. Nobody's even close to winning. It's not even close, right? This is what we call a nonpolar covalent bond. Now remember, just like in water, sometimes an atom can hold the electrons more than the other one. It didn't totally win the battle, but it's winning the battle. So when we look at a polar covalent bond, do you see, can you recognize how one of these nuclei is holding on to the electrons a little bit more than the other? So if you're, what does that mean? Do you think they would be more negative or more positive if you're holding on to the electrons for longer than the other person? More negative, right? Because electrons are negative. Pardon? Yeah. So when we look at this, it's not an outright stealing of an electron, but you have it for a little bit longer. So we use the symbol lowercase delta. This is the exact same letter in the Greek alphabet as that. This is a capital letter, and this is a lowercase letter. Just like D and D are the same thing. Would you agree with me? Yeah. That's a capital D in the Greek language, in the Greek alphabet. That's a lowercase d. Is that kind of okay? Okay. Anyways, so this represents a partial charge. So delta positive or delta negative. It's the same letter, it's just a capital and a lowercase. So remember, if you hold on to the electrons for a little bit longer than the other one, then you become a little bit positive. Not totally positive, you didn't totally win the battle for the electrons, but you're winning more than the other one. Yeah. Well. Yes, it would. Yeah, the one who's winning is more negative. And so on the symbol, I just put positive because I just decided to pick one. Okay? So that's partial. This represents partial positive charge, and then delta negative represents partial negative charge. Okay, let's take a look at an example. This is a polar covalent bond. Polar covalent bonds happen between atoms with differing or different electronegativities. So the electrons are pulled more to one side than they are the other. Let's take a look at HCl. What are the electronegativities of H and Cl? 2.2 and 3.2. So what's the delta? 1.0. So this is what we call a polar covalent bond. What does the word polar mean? It just means opposites. Yeah, polar means opposite. People can have polar opinions. What does that mean to have a polar opinion? Opposite opinions. That's all it means. But a person who is bipolar can often have opposite behaviors. It just means that sometimes they're manic, they're they're feeling very, very good or very, very high, they're very up. And then sometimes they're very depressive, which is a low. But that's what a bipolar means. It's just two opposite feelings. So, polar means opposite. So there are poles on the Earth. There's north and south. There are magnetic poles, right? North and south. There can also be electrical poles. These are electrical poles. Which one of these would you want to assign a small positive or a small negative charge to? The small negative would be the Cl. Why do you think that? It's got a greater electronegativity, so it's pulling harder. So this is a delta negative, and this is going to be delta positive. Are we okay with that? No. Oh. Yeah, we're done.